For 2 whole episodes, we've been following one electron, a single quantum arrow twisting its way down a chain of atoms. But a real piece of copper isn't one electron. Every cubic centimeter of it carries about 10 to the 23rd conduction electrons. And today, we finally pour that entire crowd into the band we built. And here's the hook I want everyone to hold on to, George. Cool that copper to absolute zero, the coldest anything can be, and the fastest of those electrons are still tearing along at about 1600 kilometers per second. Nothing is heating them, something is forcing them to move, a rule last episode's close invoked in passing. And today it gets its full episode.
That something is a single rule. One sentence about what electrons refuse to do. And my claim today is that this one rule builds an entire hidden ocean inside every metal you've touched. We call it the Fermi Sea. By the end, you'll know how deep it is, why its depths are completely silent, why all the electrical and thermal life of a metal happens in a thin skin at the surface, and how that skin dissolved one of the great embarrassments of classical physics. And the surface of this ocean is an old friend. It's the waterline we met in the closing minutes of last episode. Today, the waterline becomes the main character.
Then start with the rule, because I want to feel why it's needed at all. Here's my naive picture. We have the band from the first episode, E of k equals E0 minus 2t cosine of Ka, and the lowest energy state in it sits at k equals 0, the smooth, all arrows aligned state at the bottom. Nature loves low energy, so if I pour in 10 to the 23rd electrons, why don't they all just sink into that one bottom state? Every electron in the ground state, total energy as low as it can go, story over.
Because electrons are flatly forbidden to do that. This is the rule, the Pauli exclusion principle. No 2 electrons in a system may ever occupy the same quantum state. Notice what kind of statement that is. It's not that doubling up costs extra energy, and not that the electrons push each other apart, though they do. It's a structural fact about identical quantum particles. For electrons, a state is either empty or holds exactly 1, with no third option anywhere in nature. So when we pour in the crowd, each new electron must find a seat nobody else has taken.
And particles that live by this refusal have a family name, don't they? Say it out loud, because it's written on the front door of this show.
They're called fermions, named for Enrico Fermi. The statistics of particles that refuse to share a state were worked out by Fermi and, independently, by Dirac, which is why the bookkeeping rules are called Fermi-Dirac statistics. Electrons, protons, neutrons, fermions, every one. There's a partner family, the bosons, which do the opposite and love to pile into a single state, but they're another day's story. And yes, this podcast borrowed his name. Today we build the thing physics itself named after him, the Fermi Sea.
Before we count seats, I want to pin down what counts as a state, because I remember a subtlety from the show's spin episode a while back, the Stern-Gerlach one, with the beam that's split in 2. An electron isn't just its K label, it also carries spin, up or down, an internal arrow with exactly 2 settings. So is the state K alone, or is it K together with a spin direction?
It is both labels together, and that quietly doubles our seating. A quantum state on the chain is a twist plus a spin. K with spin up and K with spin down are genuinely different states, so exclusion allows 1 electron in each. Picture every allowed K as a little bench with exactly 2 seats, and you've earned the callback. In that Stern-Gerlach conversation, we watched this same pairing. Exclusion plus 2 spin settings, fill atomic levels 2 electrons at a time, and build the periodic table. The same rule that organizes chemistry is about to organize every metal on Earth.
Then let me do the seat count myself, because we did the hard part 2 episodes ago. A ring of n atoms gave exactly n distinct values of K inside the Brillouin zone. N sites, n twists, the head count that closed the first episode. Each twist is now a bench with 2 spin seats, so one band holds 2 n electrons in total and not one more.
2 n seats. Hold that, because now we pour. Take sodium, the classic textbook metal. Each atom donates 1 conduction electron to this band, so n atoms hand us n electrons chasing 2 n seats. The band will end up exactly half full. And here's how nature fills at absolute zero. The system settles into its lowest total energy. Exclusion forbids doubling up, so each successive electron takes the lowest seat still empty. The seats fill from the bottom of the band upward, bench after bench, 2 electrons per K, until the electrons run out. And when they run out, the filling stops dead. Every seat below 1 sharp energy taken, every seat above it empty.
A sharp line between full and empty. That's the word you slipped in at the close of last episode, the waterline. And you even gave its formal name in the same breath, the Fermi level, just before we ran out of road. So today it stops being a footnote. Define the thing properly for me.
Picture first, name second. Pour water into a valley and it settles with a flat surface. Everything below wet, everything above dry. The surface razor sharp. At absolute zero, the electrons do exactly that in energy. Filled seats up to a level, empty seats above. And that dividing level is the waterline, the Fermi level. Now the 2 names, and the distinction is small but real. The Fermi energy is the depth of the waterline measured up from the bottom of the band at absolute zero, a fixed number, a property of the metal. The Fermi level, which you'll also hear called the chemical potential, is the waterline itself in general, the level separating mostly full from mostly empty, even once things warm up and the edge goes soft.
Now catch me before I fall into what I suspect is the classic trap. When you say the sea fills from the bottom, I catch myself picturing it in real space. Electrons pooled in the bottom half of the wire like water lying in a pipe with empty metal up top. That's wrong, isn't it? Where does this sea actually live?
It's wrong, and saying why is worth a beat, because this trips everyone once. The sea is filled in K-space, in momentum, not in real space. In real space, the metal is uniform. Every K-state spreads its electron evenly along the whole chain, so the density is the same at the top of the wire as at the bottom, and nothing pools anywhere. What fills up is the axis of twists. Seats near K equals 0 go first because the band is lowest there, and the occupied region grows outward symmetrically toward positive and negative K together until the electrons are used up. For our half-filled sodium band, the filled block reaches out to where Ka equals plus or minus pi over 2, pi over twice the atom spacing, the Fermi points we found last time. One more name while we stand at the surface. The Fermi velocity is the band's slope right at the waterline, divided by h bar, the true speed of the electrons in the topmost filled seats.
So the sea has a depth, the Fermi energy, and its surface has a speed, the Fermi velocity. And there's a lovely coincidence in what you just said. For a half-filled band, plus and minus pi over 2a is exactly where the cosine band is steepest. The waterline electrons are the fastest electrons the band can offer. All right, time for real numbers. Take real copper. How deep is the sea inside an actual household wire?
About 7 electron volts deep, and that's real 3-dimensional copper. Our chain supplies the concepts, copper supplies the numbers. And that coincidence is no coincidence at all. Half filling of this symmetric cosine band always parks the shoreline, the strip of seats hugging the waterline on either side, at the steepest point. Now put 7 electron volts in scale. The thermal kick available at room temperature is kT, Boltzmann's constant times the temperature, the standard parcel of thermal energy, and a different K entirely, nothing to do with our twist, and it comes to about 1/40th of an electron volt, a tiny fraction of that depth. Said in temperature language, ask how hot the metal would need to be for thermal energy to rival the depth, and that defines the Fermi temperature. For copper, about 80,000 Kelvin, so room temperature barely registers on that scale. The sea is quantum deep. Its depth was built by exclusion, stacking electron upon electron, not by heat, and no refrigerator can drain it.
80,000 Kelvin. So on the electron's own energy scale, even a glowing hot wire is still, as far as the sea is concerned, close to absolute zero, and room warmth is a breeze ruffling the top of an ocean. The deep water doesn't know what season it is. Everything below the surface stays exactly where Pauli parked it.
That's precisely the right image, and it sets up the speed. The Fermi velocity, that slope at the waterline over h-bar, comes out for copper at about 1600 kilometers per second, which is roughly 0.5% of the speed of light. That's a few times the generic estimate from last episode. Copper's band is on the brawny end. Now collect the fact from the top of the show. That speed owes nothing to temperature, so cooling can't remove it. At absolute zero, with every thermal ripple frozen out, the electrons at the surface of the sea are still doing 1600 kilometers per second. The coldest object physics permits, and the top of the crowd is screaming along inside it.
That collides with everything classical in my head. So let me state the collision plainly. Absolute zero is supposed to mean motion stops. A classical gas taken to absolute zero is a heap of particles lying perfectly still on the floor. You're telling me the quantum crowd is forbidden from lying still. Walk me through the why, slowly.
Because lying still means everyone sitting in the K equals zero bench, and exclusion says that bench seats 2 electrons, not the whole crowd. Once those seats are gone, the next electrons take benches farther out along the K-axis, and the ones after that farther still, until the whole crowd is seated. And out to the middle of the zone, seats farther out are faster seats. The band steepens as you leave the bottom, and slope is speed. Last episode's first headline. So Pauli doesn't merely spread the crowd in energy, it forces the crowd into motion, because the only unclaimed seats are moving seats. The speed at the surface isn't thermal jiggling, it's compulsory motion, the price of a seat in a full stadium, and it survives at absolute zero because it was never made of heat. A classical gas goes quiet at absolute zero. A Fermi sea is incapable of quiet.
Now let me spring the trap I've been saving, because I know the other famous number. When a current flows in a household copper wire, the drift of the electrons, the net crawl of the crowd along the wire, is well under a millimeter per second. A garden snail overtakes your electricity. How do 1600 kilometers per second and under a millimeter per second describe the same electrons in the same wire at the same moment?
They coexist because the current is a tiny average taken over an enormously fast crowd. At any instant, half the sea flies one way and half the other at colossal speeds, and the average velocity is zero. Furious traffic, perfectly balanced, no net flow. Switch on a field, and the whole occupied block in K-space shifts by a hair, so marginally more electrons move with the field than against it. That slight imbalance is your current, and it crawls, even though the carriers of that imbalance ride the waterline, faster than any rocket ever launched. Think of a swarm of bees, each darting at ferocious speed, while the swarm drifts gently across a garden. Your reading lamp runs on the drift of the swarm, never on the speed of the bees.
Which raises what I think is the deepest puzzle of the episode. All that speed, all that stored energy, the whole crowd of them, and the sea as a whole appears to do almost nothing with it. A wire just sits there until you push it. Why is the deep sea so silent?
2 reasons, and they're the 2 faces of the same crowd. Reason 1 is a cancellation you already half know. The band is even. E of k equals E of minus k, the left-right symmetry of the chain. So at absolute zero, whenever the seat at k is filled, the seat at minus k is filled too, because they cost the same. But velocity is odd. The slope at minus k is exactly minus the slope at k, our sign from last episode. So the deep sea's velocities cancel in perfect pairs, every eastbound electron matched by a westbound twin at the same depth, and the filled bulk carries exactly zero net current. Last episode, we ran this argument on a completely full band to explain insulators. The sharper point today is that it applies to the filled interior of any sea. Even in a shiny conducting metal, the deep is silent.
Let me say that back because it genuinely reframes what a metal is. Even in a live wire carrying current to my desk, the overwhelming bulk of the sea, the deep, fast, filled interior, contributes nothing. It's motion-cancelling pairwise between K and minus K. Fine, no net current from the deep by symmetry. But cancellation is a statement about the total. The deep electrons are still down there, most of them still moving absurdly fast. So why can't one of them do anything on its own? Soak up a little heat, bounce off an impurity, make some noise.
That's reason 2, Pauli blocking, and it's my favorite of the pair. For a deep electron to do anything at all, it must change its quantum state, which means landing in some other seat. There's no such thing as absorbing energy while staying put. Now survey its options. A thermal-sized kick, around 1/40th of an electron volt, could lift it to a seat just above in energy. Occupied. Nudge it sideways in K. Occupied. Every seat within reach is taken, and the nearest empty seat sits at the surface, several electron volts overhead, hopeless for a gentle kick. So the deep electron is frozen, not by lack of energy, but by lack of anywhere to go. Only near the waterline, where filled seats and empty seats sit a whisker apart, can anything in this sea change at all.
So the entire electrical and thermal personality of a metal is a shoreline story. The deep sea holds nearly all the electrons and nearly all the kinetic energy, and it's mute, locked by symmetry and blocked by Pauli. The thin ring of seats around the waterline does all the talking. Then I know exactly what to ask next. How many seats are there at the shoreline? If the shore does all the work, the seat count at the surface decides everything.
You've just asked for the density of states, the third big idea of the day, after the sea itself and its silence. Here's the object. G of E, the number of seats per interval of energy, not per stretch of K, per stretch of energy. Keep a stadium in your head. The band is a stadium bowl. Every seat sits at some height above the pitch, and G of E asks how many seats the stadium offers at each height. Some heights are packed with seats, and some are nearly bare, and the pattern follows entirely from the band we already own through its slope.
Show me how, because my first instinct says the seats should be spread evenly. We counted them evenly in K, after all. The ring of N atoms gave a comb of allowed twists with uniform spacing, 2 pi over Na between neighbouring teeth. Nothing about that comb is crowded anywhere. So where does unevenness in energy come from?
It comes from the map between the two axes. The map is the band, and the band isn't a straight line. Walk along the K-axis in equal steps, one comb tooth at a time, and at each step, ask how much energy you just climbed. That climb is the slope of the band times your step in K. Where the band is steep, one step sweeps a large span of energy, so those seats get stretched thin, few seats per unit of energy. Where the band runs flat, a step climbs almost no energy, so seat after seat lands at nearly the same height. They pile up densely. That's the entire derivation. Seats per unit energy equals seats per unit K divided by the slope. So G of E runs as 1 over the slope of the band. Steep is sparse, flat is crowded.
Then I can read the whole stadium straight off our cosine band. The slope was 2t, a sign of Ka from last episode, largest in the middle of the zone at Ka equals pi over 2, so mid-band the seats are spread thinnest. And the slope dies to 0 at the band bottom and the band top, those flat edges we noticed in the very first episode, where the group velocity vanished. So the seats pile up at the two edges of the band.
They pile up, and in our one-dimensional chain, they pile up without bound. As the slope goes to 0 at a band edge, 1 over the slope grows past any limit, so g of E diverges right at the bottom and the top of the band. The spike has a name, the Van Hove pileup, and in one dimension it's not some tall, finite peak. The seats per energy genuinely grows without bound as you approach the edge, even though the total seat count stays finite at 2n. In 3 dimensions, the blow-up is tamed. No divergence at the band edge, just a soft square root onset that starts from 0 right at the edge. But the moral survives in every dimension. Flat stretches of band hoard states. And here's why the object earns its keep. What a material can do is largely set by g of E right at the waterline, because those are the seats the shoreline has to work with.
Let me consolidate the seat map before we heat things up. Seats are uniform along the twist axis, but not in energy. The band slope is the exchange rate between the two axes, so seats per energy runs as 1 over the slope. The steep middle of the band is seat poor, and the flat edges are seat rich, without bound in our chain, tamed in 3 dimensions. And the number with consequences is the seat count at the waterline. Now warm the sea for me, because everything so far has been at absolute 0, and no laboratory lives there.
Warmth does exactly one thing to this picture. It blurs the waterline. At absolute 0, the occupation is a perfect step. Every seat below the Fermi level full, every seat above it empty, a cliff. Turn on temperature and thermal kicks of size about kT splash electrons from just below the surface into seats just above, leaving empty seats. Hold the word bubbles just under the surface. The cliff becomes a smooth ramp, and the entire blur is confined to a skin of thickness, about kT, around the Fermi level. The ramp has a famous formula, the Fermi-Dirac distribution, the occupancy law for fermions at temperature. But its content is what I just said. Full deep down, empty far above, a soft crossover of that same thermal width at the waterline. The deep sea feels nothing. The Pauli blocking argument goes through untouched, because a thermal kick still can't reach any empty seat from down there.
So a metal never warms its electrons see through, it warms a skin. Give me the fraction then. Of all the electrons in copper's sea, how many actually live in that responsive skin on an ordinary day? I want to know what share of the crowd is even awake.
Divide the skin by the depth. That's the whole estimate, and one caveat up front. It treats the seats as roughly evenly spread across the depth. Crude but fine for an estimate. The skin is about kT thick in energy, and the sea is 1 Fermi energy deep. So the fraction of the crowd that can respond is roughly kT over the Fermi energy, and in temperature language, that same ratio is the temperature over the Fermi temperature, T over T Fermi. For copper at room temperature, that's everyday warmth set against 80,000 Kelvin, a fraction of a percent from the raw division, order 1% once the bookkeeping is done. That's the share of the sea awake at the shoreline, while the rest sleeps below, silent and blocked. Keep that 1% in your pocket. It's about to dissolve a scandal.
The scandal, set it up properly, because I've heard this described as one of the embarrassments that helped force quantum mechanics on everybody. It concerns heat capacity, the amount of energy it takes to warm something up. And the classical prediction wasn't a silly one, was it? It came from the same physics that works beautifully for ordinary gases.
It came from a theorem, which is why it hurt. Classical statistical mechanics has the equipartition principle. In thermal equilibrium, every free particle stores on average 3/2 kT of thermal energy, and it works superbly for ordinary gases. A metal, by the going model of the time, holds a free gas of conduction electrons, so every electron in that crowd should soak up its own 3/2 kT, adding an enormous contribution to the heat capacity on top of the vibrating atom's share. Measured, the electronic contribution at room temperature comes out about 100 times smaller than that prediction, roughly 1% of the classical bill. And the electrons are certainly in there. The same metal conducts magnificently, yet nearly all of them refuse to accept any heat.
And with today's picture in hand, I think I can beat you to the resolution. Equipartition silently assumes every electron is free to jiggle a little harder when heat arrives. But we've spent half this episode establishing exactly the opposite. A deep electron can't accept a thermal kick because every seat within reach is occupied. The only electrons that can take the heat are the awake ones at the shoreline, the 1%.
That's the resolution, and it's Sommerfeld's. He redid the free electron gas with Fermi-Dirac statistics, and the scandal dissolved on contact. Run the estimate with me. Only the shoreline fraction, T over T Fermi, can absorb energy, and each awake electron absorbs the usual helping, on the order of kT. So the electronic heat capacity lands below the classical guess by that factor, about 1% at room temperature, just what the measurement said. One scope note: this is the electronic part only. A solid's total heat capacity at ordinary temperatures is dominated by the vibrations of the lattice itself. So the claim isn't that metals are 100 times harder to warm than expected, only that the electron's share is that much smaller.
Does the shoreline picture predict anything you can test? Something a lab could actually measure?
It does. A clean one. The number awake grows in proportion to temperature, and so does the helping each takes. So the energy the electrons store climbs as temperature squared, which makes their heat capacity, its rate of change, linear in temperature. And the lattice's own contribution dies away much faster as you cool, so at low temperature, the electron's linear piece is left standing alone. Exactly what experiments find.
So the scandal was never about missing electrons. The sea was full the entire time. It was about a sea so deep that room temperature could only ruffle its top 1%, while classical physics sent every electron a bill for a full serving of heat. The quantum crowd pays only at the shoreline. And I notice this waterline language must also sharpen the story we ended with last episode. Metals against insulators, the copper wire against the window.
One breath of recap, because last episode earned it. We filled bands 2 per K from the bottom, and everything hinged on whether the topmost band is partly empty, a metal, or exactly full with a gap above, an insulator. And one caveat from last time: overlapping bands can turn an even count into a metal anyway. Today's refinement is to pose it as a waterline question. If the waterline lies inside a band, there's a living shoreline. Full seats and empty seats a whisker apart, so the gentlest field can tilt the sea and drive a current, a metal. If it falls inside a gap, the top band is full to the brim, and the nearest empty seat is a whole gap away. No shoreline anywhere, nothing for warmth or fields to grab. An insulator. A semiconductor is then an insulator with a small gap. Silicon's is a bit more than an electron volt, small enough that room warmth splashes a few electrons clear across into the empty band above. And doping, last episode's closing trick, plants carriers to order. The criterion now fits in one sentence. Where does the waterline sit? Inside a band, a wide gap, or a narrow one?
The copper wire and the window from last episode's send-off, one level deeper, same physics in each, and the whole difference is where the waterline landed. In the copper, it cuts through a band, so there's a live shoreline ready to respond. In the glass, it sits stranded inside a gap, a waterline with no shoreline at all, frozen out. And today supplied the why beneath the why. A field is a gentle, patient push, so it can only recruit electrons that have empty seats within reach. No shoreline, no recruits, no current.
And notice how much more the waterline buys you than the counting alone did. Every property we built today rides with it. Response to fields, heat capacity, the whole temperament of a material scales with the density of states at the Fermi level, the seat count at the shoreline, while an insulator has its Fermi level parked in a gap where G of E is 0, no seats at all. That's why it's among the first numbers anyone computes for a new material. Waterline in a seat-rich part of the stadium, a lively metal. Waterline at a thin row, a sluggish one. Waterline in a gap, an insulator, full stop.
One promised guest remains before we head for the lab: holes. Last episode we met them at the top of a band, empty seats that behave like positive particles, born out of that negative effective mass where the band curves the wrong way. You planted the word bubbles a while back, and I suspect the sea is about to swallow that story whole. Do it.
Here's the C's version. Watch it agree with last episodes in a single beat. Excite the sea. With warmth, with light, with anything. And the elementary event is always the same. One electron gets promoted from a seat below the waterline to a seat above it, which creates two objects at once. Above the surface swims a lone electron in a nearly empty stretch of band, behaving like a plain negative carrier. Below the surface floats the bubble, one empty seat in an otherwise filled sea, and it's a genuine object. Neighboring electrons keep dropping into the vacancy, which passes it upward, so the bubble rises toward the surface like air through water, and under a field it drifts as a carrier of positive charge. Now lay last episode's account beside it. Near a band top, electrons carry negative charge and negative effective mass, and the absence of such an electron behaves with the opposite of both. Positive charge, positive mass. That's precisely our buoyant bubble. Push the waterline up near the top of a nearly full band, where last episode's holes lived, and the bubble picture and the negative mass picture click into the same object. One story, above and below the waterline.
So a quiet Fermi sea plus a little energy equals swimmers above the waterline and bubbles below it. And those are the true cast of characters of a working material. Not 10 to the 23rd individual electrons, just the few swimmers and the few bubbles near the shore, carrying all the physics while the deep stays silent. Which brings us to the promise this series keeps making. Somebody can actually build this picture and point a camera at it.
Somebody can, and it's among the loveliest developments in modern physics. Take fermionic atoms, atoms whose overall makeup obeys the same exclusion rule electrons do. Cool them to a whisper above absolute zero and load them into an optical lattice, that crystal of interfering laser beams we keep returning to. The same tight-binding physics, sights and hopping, every knob under control. The atoms fill the band precisely as we described, from the bottom up, seat by seat, and assemble a real Fermi sea in front of you. One difference from our uniform chain, the atom cloud sits in a trap, a shallow bowl, so the deep-filled sea shows up in real space too. A central plateau locked at full occupancy. Then comes the instrument that changed the field, the quantum gas microscope, which photographs the lattice site by site, so you can watch the filling directly. Exclusion flattening the cloud's middle into a plateau of fully occupied sites, the sharp, cold edge, and that edge blurring into the Fermi-Dirac ramp as you warm the gas. The Fermi sea, imaged atom by atom.
And that's the same family of machines our cold atom episodes keep visiting. A chain of light with a tunable hop, and now a sea you can photograph swimming inside it. 2 episodes ago, that lattice was a stage for one atom. Today, it holds a filled, imaged sea that matches the whiteboard line by line. All right, George, bring it home. Give me the whole episode as one arc.
3 ideas, 1 ocean. First, exclusion, no shared seats, 2 spins per twist, fills the band from the bottom up to a razor waterline, and the sea it builds is quantum deep and quantum fast. 7 electron volts down, 80,000 Kelvin as a temperature, 1,600 kilometers per second at the surface, standing at absolute zero, none of it owed to heat. Second, the deep sea is inert. Velocities cancel between k and minus k, and Pauli blocks every exit. So the whole life of a metal happens in a skin about kT thick at the shoreline, a fraction T over T Fermi of the crowd, which is why the electron's heat capacity comes in about 100 times under the classical bill. Third, the density of states, seats per energy, 1 over the band slope, says how generous the shoreline is, hoarding seats at the flat band edges and thinning out mid-band. Depth, silence, seats. That is the Fermi sea.
Then let me say the whole journey back, just the pieces your list leaves out. My desk lamp runs on the snail-pace drift of a supersonic swarm, the whole current a slight lean in a furious cancelling sea, and metal against insulator against semiconductor collapsed into one question. Does the waterline touch seats, or is it stranded in a gap? One rule: no 2 electrons in the same state. Did all of it.
Which leaves the door we have to walk through next time. Everything in this series so far rests on one quiet assumption: 1 orbital per atom, hence exactly 1 band. And last episode, we saw how real atoms stack more bands above it, and how magnesium and calcium sneak into metalhood when those bands overlap. But notice what we've never actually done: built a gap. We've pointed at gaps, gestured at where they sit, and helped ourselves to one in the story of silicon. So next episode, we manufacture one from scratch, with the simplest crystal that can do it: a chain of 2 alternating atoms. Call them A and B, a deep well then a shallow well, the diatomic chain. Out of that one change, our single band will split in 2, and a true forbidden gap will open up between the halves, and you'll see exactly what a gap is made of. Same arrows, same hopping, 1 new ingredient.
A crystal with a heartbeat, 2 atoms repeating, and out of it falls the gap that the entire electronics industry lives inside. I can't wait. Until then, here's your homework image. The next time you switch on a lamp, picture what's really inside the wire: a sea 7 electron volts deep, utterly silent in its depths, its surface racing at 1,600 kilometers per second, and every bit of the useful work done by one thin, bright shoreline. Thanks, everyone. Come back for the diatomic chain. 2 atoms per step, 1 gap, and a whole new floor of the subject to stand on.